So again, we talk about parent functions, and we're looking at the most basic one, linear. So if we plug in -2 for our x value, of course our y value equals that exact same thing, so -2. Plug in -1, I get -1, 0, I get 0, and 1 and 2. So if we plot those 5 points, -2, we're at -2, -1, we're 1, 0, 0, 1, 1, and 2, 2. We've got our function there, or our line. So what is its domain? How far to the left, and then how far to the right do we go on our x values? If we look at it, we're never going to stop going to the left. So using our interval notation, we're going to -infinity, and then we're going to the right. We don't have any breaks. We have that arrow pointing to the right, so we're going to positive infinity on our positive x values. Our range, same thing. As we move down, we've got that arrow, it's going to point down, it's going to keep going down, so we're going to -infinity, and our range is also going up to positive infinity as we move to the right side of the graph. Then we want to look at our x and y intercepts. Our x and y intercepts are going to be the exact same on all of these graphs, on all of these parent functions. They're going to be at 0, 0, right? They're going to go through the origin because we're not doing any transformations. We're not doing any translations up, down, left, or right. So our x and y intercept is always going to be through the origin for our parent functions. Now the maximum number of zeros, or they say on their roots, we're talking about x-intercepts. How many x-intercepts are possible, or the maximum, when we're dealing with a linear function? 1. Right? We can only ever have 1. We could have none if we have a horizontal or flat linear function with a slope of 0 that we've shifted up or down. But at most, we're going to have 1 x-intercept. Okay? What about our end behavior? As x approaches -infinity, f of x, or our y approaches what? So -infinity, we're going to the left side, so we're going down. So we get -infinity, right? So as we move to the left side, our arrow is going down, we're going to -infinity. As we go to the right side of the graph, so as x approaches positive infinity, f of x approaches positive infinity as well. Right? They're both going up. We have an increasing graph. And then the last thing, is this continuous or discontinuous? Continuous, right? As soon as we get in our domain, there's no breaks in our graph. We are continuous. Okay. Our second function we're going to look at, or our second parent function, is absolute value. And that is just y equals absolute value of x. So again, put it in our xy table. If I plug in -2 for my x value, what do I get? 2. Right, the absolute value of -2 is 2. Absolute value of -1 is 1. Absolute value of 0, 0, and 1, and 2, right? Absolute value is referring to distance from 0, so it doesn't matter if you're on the left side or the right side, you're only ever going to get back a positive answer, right? Absolute value cannot be negative. So then, if we graph these at -2, I'm at +2 on the y, -1, I'm at +1. 0, 0, 1, 1, and 2, 2. So we have this V shape. Our domain is going to be what? Negative infinity to positive infinity. Our range, however, has changed. What is our range now? 0 to infinity, and we include 0, so we're going to put a bracket around it. And of course, go into infinity, always put that parentheses. Our x and y intercept, again, still 0, 0. But what about our maximum zeros? Looking at this graph, if we were to manipulate this function, if we were to move it around, what would be the maximum amount of zeros that we can get? So like say if we shift it up, how many times are we going to cross that x-axis? 0 times. What if we shift it down? 2. So our maximum amount of zeros is 2. All right, if we move this down, I'm going to cross that graph in 2 spots. Or cross the x-axis in 2 spots. The next thing is end behavior. So as x approaches negative infinity, f of x approaches, are we going up? So positive infinity. As x approaches positive infinity, f of x approaches positive infinity. Is this graph continuous or is it discontinuous? Continuous, right? Again, we don't have any breaks in our graph. So then let's look at our next function. What is the equation of our quadratic function? Anybody know? X squared, right? I heard somebody say it. X squared. So that is our most basic quadratic function. So if we plug it into our xy coordinate plane, if I plug in -2, what is my output going to be for my y? 4, right? If we square something, we're essentially multiplying it by itself 2 times. So -2 times -2 gets us a +4. So -1 squared is 1, 0 squared, 0, 1 squared is 1, and 4. So they repeat. So when we graph this, -2 for +4, -1, 1, 0, 0, and 2, 4. Notice though, on this one, we don't come down to a point like we did on our absolute value. We have that rounded U shape. So that is our parabola shape. Again, x and y intercepts. Still at 0, 0. I forgot to do, our domain is going to be what? Negative infinity to positive infinity. What is our range going to be? 0 to infinity. So that is just like our absolute value sign for our domain range and for x, y intercept. What about our maximum number of zeros? What do we think that is? 2. Right. Just like our absolute value, what do we think our end behavior is going to be? So as x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, f of x approaches positive infinity. And are we continuous? Yes, we are. So the maximum zeros, again, are how many times we're going to cross the x-axis. How many possible times. So in this graph, they only have the 1. But they're talking about maximum zeros for all quadratics. So this is the one thing we're not looking at just this graph. Okay, we're talking about if we move this graph around, how many possible zeros do we have? So if we shift it down, that would put our u, or our quadratic, down here, and then we would cross the graph twice. So there's our possible 2 x-intercepts. Okay. So really, we have 2 as our maximum. We have a possibility of 1, like we have there, where we just touched. And we also have a possibility of 0. If we had shifted our graph up, right, then we'd have 0. So we have multiple possible zeros for each. Okay, so then let's flip to our next page. Let's look at our cubic function. So anybody know what the equation of our cubic function is going to be? X cubed. Right? We're not very creative as math people, so we call things generally what we call them same function. So cubic is x cubed, or x to the 3rd power. Our xy table. -2, -1, 0, 1, and 2. If I plug in -2 into x cubed, what do I get? -8. Right? It's -2 times -2 times -2. -2 times -2 gets you 4, times -2 gets you a -8. -1 cubed is going to get me -1, 0 cubed, 0, and then 1 cubed, 1, and then 2 cubed will be 8. Okay, so if we graph these at -2, I'm at -8. -1, I'm at -1. 0, 0, 1, 1, and 2, 8. So there's my graph for this one. Okay, I have that little kind of S shape. It's not very S-shaped in this, but we can move these kind of dips to where we have a min and a max. What is our domain going to be on this? How far to the left can we go? Negative infinity. We can go all the way to the right, so positive infinity. What about our range? How far down do we go? Negative infinity. Again, go up towards positive infinity on our y. X, y intercepts. Again, 0, 0. Maximum number of zeros. So on this graph, we have 1. Anybody else want to take a guess at how many our maximum is going to be? 1 is not our maximum. It's how many we have on this graph. So let's think about it. Quadratic, we had 2. 3. 3 is our maximum. And the way that happens is if we stretch out these kind of little flattened out parts, we can get a curve that looks like this. Our endpoints mimic our parent function of that x cubed. So we can actually stretch out those parts and make some local minimums and local maximums. So we cross that graph where that x-intercepts being 3. So that x-axis cross it 3 times. Then our end behavior, as x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x positive infinity. And is this one continuous? Yes, it is. Then our last one is our square root function. So our square root function is we're going to take the square root of x. Sometimes this is also called the radical function because this is our radical, that little shape. What happens if I plug in -2 into a square root? Think back to the very, very, very start of the year. If I plug in -2, it's not a fraction. It's not irrational. It's another I word. SpongeBob. It's imagination. It's imaginary. Right? If we take the square root of a negative number, it's an imaginary number. So we don't have those values on our regular, real XY coordinate plane. However, if we have real numbers, or whole numbers, I should say, so 0, if I plug in 0, square root of 0 is 0. Square root of 1 is 1. Square root of 4, so I changed it, it's 2. I didn't want to take the square root of 2. I was just going to use whole integers there. So if I graph this, those negative numbers aren't going to be on my graph. They're just non-existent there. But we do start at 0, 0. We have 1, 1. And at 4, we're up at 2. So here's kind of our graph. It's kind of coming up, and it's leveling out. But what is our domain going to be for this one? What's the farthest to the left that we go? 0. How far to the right do we go? Infinity. What about our range? What's the lowest value that we have? 0. How high are we going to go? Infinity. Right? We have that arrow still going up. Although it's getting a little flat, it's still going up, right? If we go out to 9 on our x value, then we'll be at 3. If we go out to 64 on our x value, we're going to be up at 8. So it's still increasing, just very slow. So it is going to make it to infinity. So our end behavior, or what xy intercepts, I should say, are going to be same thing, 0, 0. Our maximum zeros, 1. We can only ever cross that x-axis one time. And then our end behavior. As x approaches negative infinity, f of x approaches what? Well, do we have one? No, we just don't even have one in this case, right? As soon as we go into that negative area, we don't exist anymore. We're in the imaginary realm. We're not a part of it. But as x approaches positive infinity, f of x approaches positive infinity. Is this one continuous?
No. Yes. It's continuous on one end.
So once it starts, it's continuous. So in that case, it's going to be continuous. Okay. We are continuous once our domain starts. And we could manipulate it enough if we wanted to where it would be discontinuous, but we're not going to talk about that at this time. For our most basic square root functions, they are continuous. Yes? They're just stretching. All right, so the next page on the notes is actually what we're going to do, not today, but later. When? Thursday. I'll take another video of it and upload it. So. Does that work? So that is our parent functions. Now we're going to actually look at our absolute value functions. So remember these parent functions, we're going to get to them throughout the year, but we're now going to look at our absolute value functions kind of more in depth. We've been working with linear. Now we're going to look at absolute value.
We don't have that.
I'm about to hand it out to you. Okay, so looking at our absolute value functions, we're going to look at first by solving them. So again, absolute value is talking about distance from zero. No such thing as a negative distance. Doesn't matter if I'm on the left side of zero or the right side of zero, it's still going to be a positive distance. So here's some examples. The absolute value of 3 is 3. The absolute value of negative 3 is 3. The absolute value of 0 is 0. Right, we're just on our origin, we're on that 0. The absolute value of negative 5 is 5. So because of that, we're kind of going to have two answers, right? When we're talking about absolute value, solving absolute value equations, we can have both a positive answer and a negative answer that both result in the same distance of 3. So we're going to have to take that into account whenever we solve these equations. So the way we do that is, first off, we have to set our absolute value equal to some number. So we have to solve for the absolute value first. So in this case, we have x plus 3 minus 8 equals negative 5. So they're going to add 8 over. So then we have the absolute value of x plus 3 equals 3. So we have to isolate that absolute value. The second step is we want to set up one positive and one negative absolute value. So we have x plus 3 equals positive 3, and x plus 3 equals negative 3. And once we've done that, now we solve for x in both of our equations. The nice thing is, whatever you use to solve for this x, you can use those same steps to solve for that x. So we would subtract 3, we get x equals 0. Subtract 3, we get x equals negative 6. Once we have these values, we can check to make sure those are true solutions to what we started with. You can plug them in, right? So 0 plus 3, take the absolute value of that, we get 3 minus 8 gets us that negative 5. Or if you plug in negative 6, negative 6 plus 3 gets you negative 3, take the absolute value of that, you get 3 minus 8 gets you negative 5. So both of those check out. Special note, again, absolute value is talking about distance. You can't be equal to a negative distance. So if you have a number like this, where we have the absolute value of 2x plus 5 equals a negative 18, it's not possible, right? We cannot have a negative absolute value. So that's not possible. However, we could make it possible if we had a negative number out front. In which case, to get this negative, or to move it over, we would have to divide by that negative 2, and then that would leave us with the absolute value of 2x plus 5 is equal to 9. That is possible. Right? Then we would solve just like we did the one above it. So again, if you have an absolute value equal to a negative, you can stop right there. You don't have to solve. It's just not possible. But if you haven't isolated it yet, and you have that negative multiplication or division out front, we need to change and isolate it, because you may end up with a positive answer. then you have to
So I
solve.
put my rain jacket in here.
Yes, you
Yes,
did.
sorry.
Okay, so let's look at a few of these practice problems. Letter A. We've got the absolute value of x equals 8. So what can x equal? 8 and negative. Right? We just set that one up and solved it for us. B. We got the absolute value of x minus 2 equals 5. So again, we have our absolute value isolated. So we say x minus 2 equals 5, and x minus 2 equals negative 5. So we solve for x. Add 2 over, we're going to get x equals 7. Add 2 over, x equals negative 3. And again, we can plug these values right back in, make sure they work. 7 minus 2 gets you 5. Negative 3 minus 2 gets you negative 5. Take the absolute value of that, you get 5. Right? So on all these absolute values, you're going to have 2 answers. Okay, you're always going to have 2 answers. So pick one off the back page, or pick a couple. What do you want to do? F.
I don't know if it's doing this one. It's a little letter. I didn't do that.
So F, we've got negative absolute value of 3x plus 2 plus 8 equals 14. First thing is we have to isolate this absolute value. So we're going to subtract 8 from both sides. So that's going to get us 6. And then we have to get rid of this negative, right? We cannot have the absolute value, we cannot solve until it's isolated. So divide by negative 1, that gives us absolute value of 3x plus 2 is equal to negative 6. And at this point, we can stop, right? We've isolated our absolute value. It's equal to a negative number. There's nothing else we can do. This one is just not possible. Right? Again, we cannot have a negative distance. If there's a positive 6 we could solve, but we can't have that negative distance. Are there any others? H. So let's look at H. Yes, so subtract 10 to begin with. So subtract 10. It says 12. That's minus 2. And then we have this negative 4, and it's being multiplied by our absolute values. So opposite of multiplying, division.
It's not possible.
So we're going to get a negative 3, so then again it is not possible.
So what I'm getting at is, it's negative, like, if it's a negative, like, on this side, and then on this side.
Could be.
Unless there's a negative behind equal sign, then it is possible.
Yes. So it just depends on what steps you have to take to get that isolated, that absolute value isolated. If it ends up with negative, it's just not possible. That might not always be the case.
That makes sense.
Okay. Any questions on that? So that's the homework for today, absolute value equations.